So in this video, we're going to talk about IP address classes and masks. So in order to really understand this, we have to talk a little bit about the history of IP. And way back in the dark ages, back in the early 1980s when IP was first invented. So we know that when IP was first invented, among many things, the designers of IP said, okay, we want this to be a routed protocol, which means every node has to have an IP address. We know that they decided that the IP address would be 32 bits long, so it would be represented in binary as 32 bits, some combination of ones and zeros. We also know that as a routed address, they decided that part of that address would be the network, part of it would be the node or the host. And the network portion, all the devices within that same area of the network would share those bits in common. Now, one thing the designers of the original IP had to decide was, of this 32-bit number, where's that dividing line going to fall between where the network portion that all these hosts share is the same and the rest of it, which is like a unique serial number, a host ID for the host. So the original way they did it was very simple. They said, okay, we know that we're going to represent these as dotted decimal addresses. Each byte is going to be separated by a dot. They said, well, here's what we're going to do. Because remember, this is way before the days of the internet. The internet wasn't even developed back then. They said, we're going to break IP addresses into 3 classes of addresses. In one class of address, the very first byte will represent the network. So if your particular device, laptops were not invented back then, but let's just imagine that back in the early 1980s they had laptops, okay? One came back from the future. So somebody sitting with a laptop would say, okay, I'm going to put an IP address on my system. And if the IP address falls into this category, my system will know that the very first number is the network that I'm in. And all the same people in my network, like maybe I'm in payroll, all the other people in payroll will have that very same number to begin with. And then the remaining 3 bytes, 24 bits, are going to be unique just to me. And they said, okay, we're also going to have another different type of address, class of address, where the first 2 bytes represent the network. And then there's 2 bytes left, 16 bits, for host addresses. And then guess what? We're going to have a third class of addresses where the first 3 bytes represent the network that everybody's sitting on. And there's only 8 bits left to represent the node address or the host address. And this is what they called classful addresses. This first one is what they called Class A addresses. And you can probably guess what this was, Class B addresses. And this was Class C addresses. Now here's a question that you might be wondering. You might be saying, okay, Keith, but let's say that I'm back on a huge computer back in 1985 and I put an IP address on my computer. Just based on that 32-bit number, how does my computer know which of these 3 classes that particular address falls into? Well, they had a very simple system for that. They said, remember, the computer is looking at the IP address as a 32-bit number, not as decimal numbers, but as 0110000 blah, 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 blah. That's how it sees the IP address. So the computer knows, based on that 32-bit number, which class of address it is in based on a very simple code. In binary, if the very first bit starts with a 0, you're done. That was a Class A address. It didn't matter what the remaining 31 bits were. If the very first bit was a 0, that computer knew my first byte is my network. And everybody on my network shares that same combination, that byte. If the computer saw that the first 2 bits were 10, followed by anything, 10 anything, it said, okay, I know that my IP address is a Class B address. Now I know that the first half of it represents my network. And then if it saw this pattern, 110, it said, oh, okay, now I know that my IP address is a Class C address, meaning that the first 3 bytes out of the 4, 3 bytes represents the network that I'm on. Now this is way back in the day before subnet masks were even invented. Subnet masks were not even a thought back then. This is the way the early designers decided to create IP, divided into 3 classes, and the class, based on the bit pattern at the very beginning, would determine that dividing line between where the network portion of the address ended and where the host portion of the address began. And so that's how it was determined with class A, B, and C. So let's think about this here then. Class A address, we know that it starts with 0 dot anything. So, you know, that would be our smallest class A address, which is 0000. Or technically speaking, the largest class A address, I have to reduce my font here even more to fit this in. The largest class A address would look like this. It would have to start with a 0, and then every other bit after that would be turned on. Now remember in the previous video I said that there were some bit patterns that you should be able to look at and instantly recognize what they are? This is one you're going to see over and over and over again. 8 bits of continuous ones. And hopefully you remember that was the number 255. However, remember in a class A, we don't even really care about these last 3 numbers. They could be anything because that's the host identifier. That doesn't even belong to the network. So actually what I'm going to do is I'm going to do this. So the smallest class A would be 0 dot anything. The largest class A, because it has to retain that bit as a 0, would be 0, 1, 1, 1, 1, 1, 1, 1. Well, what's that number? Now you could sit back and say, oh my gosh, I got to add all that up. 1 plus 2 plus 4 plus 8. You could do that. Or remember, binary goes in patterns. If I have this, the next number is that. What's the next number after that? Well, then we put that back into a 0 and we turn the next spot on. Then what's the next number after that? 1, 1. Then what do we have? Then we have 1, 0, 0, followed by 1, 0, 1, followed by 1, 1, 0. So if I gave you a number like this, okay, and I said 0, 1, 2, 3, and I said, what is that number? Well, you could say, all right, that's 1 plus 2 plus 4. And you'd say, that's the number 7. And you'd be right. But if we think about the pattern of binary, the number just before that was that, right? What's the number just after this? The next highest number. Isn't it 1, 0, 0, 0? If you look at that number, isn't that pretty easy to figure out? Well, there's only 1 bit turned on, and that's in the 8 position. So if this number right here is the number 8, then backing off by 1, this has to be 7. So how does that help us with this? Well, remember those bit patterns I talked about? If I've got 0, if I have that, what's the next highest number in binary if I add a single bit to that? Wouldn't it be this? Isn't that it? And that one should be pretty easy. The only bit turned on there is the 128 bit. So therefore, if we back off by just 1, this has to be 127. So technically in the class A range, 0 dot anything is the smallest class A, and 127 dot anything is the largest class A address. Now in another video that we're going to get into in a little bit, we're going to see that some of these IP addresses are actually reserved for special uses. For example, 0 dot anything and 127 dot anything are actually reserved, but they technically fit into the class A space because 0, 1, 2, 3, 4, 119, 113, all the way up to 127, what do they all have in common? This bit, the very first bit, is a 0, which makes them class A. Now if we look at class B, we can do the same type of thing. The smallest class B address would be 10, let me do this, dot anything dot anything dot anything. So that is 128. I'll put this up here. 128 dot, I'll just say XXX, because those X's could be any number. And what's the largest class B? Well, it still has to retain 10 at the beginning, but then 1, 2, 3, 4, 5, 6 dot any dot any dot any. All right, well, once again, this is kind of a hard number to add up, but think about the pattern of binary. What is the next largest number after that? Isn't it this? 1, 1, and then 1, 2, 3, 4, 5, 6. Isn't that the next largest number? Shift all these to zeros and move the next one over. Well, that is the number 192. Therefore, this here has to be one less than that. 191.any.x.x.x. So class B space begins with 128, that's the smallest class B address, and ends with 192. So back in the old days of 1985, 1986, before subnet masks were invented, if you put an IP address on a system that was anywhere in this range, 128, 137, 145, all the way up to 192, it knew, by looking at the first two bits which were 1, 0 in binary, it knew that the first octet and the second octet belonged to the network, and the remaining bits were host bits. And then lastly, with class C, we know the smallest address would be this. So that is the number 192. This is not 192, this is 191. 191.any dot any. There we go. Okay, didn't do my math correctly. 191. This is 192. So 192 starts the class C range. And what's the largest number we could come up with? Sticking with 110 as our pattern. 1, 2, 3, 4, 5. Dot any, dot any, dot any. Well, we say, okay, well, that's kind of a hard number to add up. What's the next number in the binary pattern? The next highest number would be that. And that number is 224. So therefore, this right here is 223 dot anything dot anything dot anything. So these are the ranges of class A addresses. Now if I go to the slide, that's exactly what we have right here. You might say, well, wait a second, Keith, I see class D and class E. You didn't talk about that. Well, those classes form the exact same patterns. So remember, class A was 0. Class B was starting with a 1, 0. Class C was 1, 1, 0. In binary, how do you think you would recognize a class D address? It'd be 1, 1, 1, 0. How do you think you'd represent a class E address in binary? 1, 1, 1, 1, 0. So this is how, back before subnet masks were invented, how devices knew what their IP addresses were. Now these two right here, class D and class E, these were reserved for special use. So class D was used for multicast, and still is to this day. Class E was experimental, and I've honestly never seen a device that had a class E address. So all hosts, whether it be your smartphone, your laptop, your tablet, whatever, are going to have some address in this range here, between a class A and a class C. Now, in today's networks, IP addresses come alongside with subnet masks. This is the old way. You might be saying, well, Keith, if they don't do it this way anymore, why do we have to learn about this? Understanding classical addressing and how they're represented in binary is actually very important, especially in the world of IP routing protocols. Especially when you get to, for example, the CCNP level, when you start doing things called route summarization and things like that, you have to understand what these classes of addresses are. And I'm going to be referring to these. I'll say, oh, that's a class A subnet, or that's a class B subnet. You'll hear me say that over and over again. Class A, class C, class B. And if you didn't know what those classes meant, that'd be useless to you. That'd be meaningless information. So moving forward, you should be able to go into the ICND1 exam and given any IP address, you should be able to identify what class of address that would be. Let's do some examples of that. Let's just do some exercises to see if you've got that. All right, so examples. Okay, so I'm going to give you some IP addresses, one at a time, and I want you to identify which class of address is the one shown below. All right, so here we go. I'm going to give you some addresses, and I want you to pause the video, identify the class of address, and then resume the video. Okay, what class of address is that? Okay, hopefully you answered correctly that that is a Class A address. Now there was two ways to do that. You could either have memorized these ranges. You see that 5 falls in the Class A range. Or what you could have done is you could have said, okay, well the number 5, if I take a look, is the 128-bit on or off? 128-bit is off. I'm done. That's a Class A address. I don't even have to convert the number 5 into binary. Once I knew that the 128-bit was off, bam, I'm finished. That's a Class A address. All right, let's do another one. What class of address is that? Okay, hopefully you said that is a Class C address. Once again, you could have done it from memorizing the ranges. That falls in the Class C range right here. Or you could have done it by this way. Okay, 204 is the 128-bit on or off. Yes, 120 is definitely part of 204. What about the 64-bit? Well, 128 plus 64 is 192, so yes, the 64-bit is on. Is the next bit, is the 32-bit on? Well, 192 plus 32 would be 224, so the 32-bit is off, and I'm done. If it starts with 110 in binary, that is a Class C address. Let's do two more. What class of address is that? Okay, hopefully once again you said that was a Class A because the 128-bit is off, and with the 128-bit off, you're done. That is a Class A address. What about this address? Well, hopefully for that one, you said that is a Class B address. And how do we know? Well, because the 128-bit is on. But if we turned on the 64-bit, 128 plus 64 is 192. That's too high. So the 64-bit must be off. And then we're done. This is a Class B address because the 128-bit is on and the 64-bit is off, making that Class B. All right, let's talk about subnet masks. So back in the early days of IP addressing, back in classful addressing, there was no need for a subnet mask. A system, a device would just simply look at those first few bits and it would know where the boundary line was between the network portion and the host portion, just simply based on the class of address, A, B, or C. But as time evolved and devices and universities and companies started connecting more and more to the internet, the designers of IP realized, well, wait a second, we're going to start running out of addresses here. I mean, let's think about Class A, for example. Look at Class A. Now, technically, in the Class A space, not all of these are usable. Class A, technically, the very first usable address is the 1 network. And we'll talk more about reserved addresses in a future slide. And then the last usable address is 126 dot anything. So there's only 126 Class A addresses, and those got consumed very, very quickly. Very quickly, they were all used up. Class B addresses, well, there's more of them because the first 2 bytes are usable. So there's quite a few more. So there's 128.0, that's a Class B. 128.1, that's another Class B. 128.2, all the way up to 128.255. before we even have to go up to 129 dot anything. 129.0, 129.1, 129.2, all the way up to 129. So there's a lot more of them, but still, as the internet started growing and people started, getting more and more addresses, this classful addressing scheme wasn't going to work. As a matter of fact, we probably would have run out of addresses if they'd stayed with Class A back in like the early 90s, like 91 or 92. They probably would have all have been gone. So they said, okay, we have to do something different here instead of classful addressing. So we're going to do something like this. We're going to say that a device, I'm not counting here, let's just assume that that's 32, I'm not counting it up. An IP address is still going to be 32 bits long. However, when that device obtains an IP address via DHCP, or because you've configured it manually, you're going to have to provide one other bit of information. Because now we're going to say you can draw the dividing line anywhere in the IP address. It's up to you as the network administrator whether you want the first 8 bits to be part of the network, or the first 15 bits, or the first 22 bits to be the network. It's completely up to you. You could say, well, I want to do this. Now, once again, I'm not counting here. I'll count in just a second. So what is that? Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I think this is something like 18, if I've got it correctly. So I've just arbitrarily decided that the first 18 bits were going to be my network, and the remaining bits, the remaining 14 bits, were my host identifier. And this is why we need a subnet mask. Because if I now have the ability to arbitrarily set my dividing line between the network portion and the host portion anywhere I want, the computer, the tablet, the smartphone has to have a way of knowing where that dividing line is. Because this is now what's called classless addressing. I'm now saying, look, the first few bits, meaningless. You can no longer look at whether it's a 0 or a 10 or a 110. That's not going to tell you anymore where the network dividing line is. In classless addressing, the only way to tell where the network dividing line is by providing a subnet mask. And subnet masks can take one of two forms. They can either take shorthand form, which would look like this. So if you ever see an IP address that looks like this, so this portion of it with the backslash, or actually it's a forward slash, yeah, with the forward slash right there, that is the subnet mask. What that's telling you, what that's telling the system, so whenever I put this IP address on something, a laptop or a router's interface or whatever it is, this is saying that of this 32-bit number, the first 28 bits are the network. In this case, the first 18 bits are the network. So a lot of times in papers and documentation, when people are writing IP addresses, because now we have to include a subnet masks are usually written this way: /28, /20, /8, /16. When you actually configure an IP address, though, you can't configure it like this. You actually have to configure it in dotted decimal. So for example, let's just do something simple. Let's say that I had this IP address. All right. Now, what class of address is it? If we were talking about classful addressing, what class of address would that be? Hopefully you said, that's a Class A address, Keith, because the 128-bit is off. That's correct. Now, as a Class A address, how many of those numbers are referencing the network portion of the address? Well, hopefully you said, well, Keith, in a Class A address, the first byte represents the network. That right there. Okay, so in a Class A address then, what you're telling me is that the first 8 bits represent the network. And that would be true. The first 8 bits represent the network. In a Class B address, well, in a Class B address, the first 16 bits represent the network. So we could say /16. And in a Class C address, the first 3 bytes, the first 24 bits, represent the network. So these are what are called default or classful masks. Classful masks because they're not breaking the classful boundaries here. And that's what we see here on this slide. The default subnet mask for a class A is a /8 or 255.0.0.0. You say, wait a second, how do we get 255 out of that? Remember, a /8 means this. It means in dotted decimal 1, 2, 3, 4, 5, 6, 7, 8. It means the first 8 bits are networking bits, and then everything else is not. So this number right here is 255. That's one of those numbers I said you need to memorize. A /16, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and then all zeros. So that is 255, 255. That's where we get that. So this is actually the way when you're configuring an IP address on an interface, in addition to the IP address itself, you have to configure the subnet mask as dotted decimal. So just like the IP address is dotted decimal, 101.17.4.6 dotted decimal, you would then have to provide the subnet mask, 255.0.0.0. And the way the computer system uses this subnet mask, the way it works it, is it says, okay, 255. It says that's 1, 2, 3, 4, 5, 6, 7, 8. So the computer system says, this subnet mask is telling me that the first 8 bits of this number are the network. Well, the first 8 bits are 101. If my subnet mask had been this, 255.0.0, applied against the exact same IP address, well, then the computer system would say 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So the computer system would say, oh, okay, of this IP address then, he's telling me that the first 16 bits belong to the network. 101.17 belong to the network. So that's why the subnet mask is critical. It's paired up against the IP address. Another way sometimes that I've drawn it just to help you visualize this is something like this. So if I gave you an IP address in binary, I'm going to do a real easy one. Okay, so first of all, how would you represent that in dotted decimal notation? Hopefully you can very easily say that address is 3.1.2.1. Okay, now if I want to provide a subnet mask against this, a subnet mask that indicated that the first 16 bits should be part of the network. Let's say this is payroll, and all the people in payroll, their IP addresses are all going to begin with 3.1. Everybody in payroll is going to start with 3.1 because they're on the same network. Well, then my subnet mask would have to look like this. So if you actually line the subnet mask underneath the IP address, you can see that there's a correlation. Whenever a bit in the subnet mask is turned on to a 1, the corresponding bit in the IP address is called a networking bit. So in this case, we're saying, okay, all 8 bits of the first byte are networking bits. They belong to the network because all 8 bits of the first byte of the subnet mask are turned to 1. All 8 bits of the second octet are turned to 1, so all 8 bits of this are the networking bits. So the way that we would actually represent this here would be 255.0.0.0. Got to remember my dot right here. So we would say 3.1.2.1, 255.255.0.0. We'd line it up this way. And this portion right here is the subnet mask, and that's telling us that the first 16 bits of this address belong to the network. So that's why all modern systems today have a subnet mask paired up with their IP address, because that tells the system where that dividing line is between network and host.